Hello everyone, you are welcome back to class. So this is part 2 of the general material balance equation class. So I'll be going through the outline once again. You have reservoir types, the general material balance, reservoir drive mechanisms, the Schilthius material balance equation, Avena and Ode derivation. So in the part 1, we discussed the reservoir types and introduction of general material balance as well, and reservoir drives. So I'll quickly go to slide 19, where we'll continue for the part 2. Um, we'll be looking at the terms in general material balance equation adopted by the Society of Petroleum Engineers. You have your P high initial reservoir pressure, to your bulb point pressure. You have all these, so please just look through them and their units, specifically your NP, cumulative oil produced, STB, your water produced, your GP is in SCF, that's your gas. You find measure your gas in SCF, standard cubic feet. Your NP are your oil producing stock time barrel. This is STB, stock time barrel. SCF is standard cubic feet. Your change in pressure is P high minus P. This is the initial reservoir pressure, and this P at every other pressure, okay, as pressure drops during production. Then I'll come down here to your GOR, instantaneous gas oil ratio. You have your RSI, initial gas oil ratio, your gas solubility, okay, in SCF by STB, okay. And then you have your BO high, initial formation of volume factor in barrel per STB, your BO in barrel per STB as well, BGI, barrel per SCF, your BG. BGI is the initial gas formation volume factor, like your BO high, also the initial oil formation volume factor, as in barrel per STB. This is your VR over VSC, as reservoir volume over volume at standard condition. Your BG high, that's your also volume of your gas at a reservoir volume over standard condition volume. So you have your BG at every other pressure, barrel per SCF, your water injection, your gas injection, gas in SCF, water in STB, and you have your water injection and gas injection when you have pressure maintenance. You see this as you go on. You have your WE, that's your water influx from your aquifer. I'm sure you're familiar with that already. Your M is your gas cap size. Your G is your initial gas cap. Your M, barrel per barrel, so it is dimensionless. It's the gas cap size. And then your G, initial gas cap gas, SCF. Your pore volume, you see PV, pore volume. Water compressibility, you're familiar with this already. You have your CO as well, oil compressibility, your CG, gas compressibility. Your CF is the rock compressibility, all in per PSI, per PSI. Okay, so derivation of the material balance equation. Okay, what happens? You have when your oil and gas is tapped, oil, gas, and water is produced, thus reservoir pressure reduces. I'm sure you know this already. So when you have production of your oil and your gas, there is a drop in pressure, okay? And because of this drop in pressure from your initial pressure, initially you can be able to maintain the reservoir pressure, the pressure of your reservoir within the initial pressure and the bulb point pressure. So in between this, you have the undersaturated zone. I'm sure you can recollect this from the previous classes that we've done, the undersaturated zone. So in that undersaturated zone, you can maintain your pressure with minimal pressure drop. Okay, the remaining oil and gas expand to fill the space removed. Okay, so this void space, your pore volume, as oil and gas is produced to the surface, the remaining oil and gas expands to fill the surface because there is no void space at all. So oil and gas expands as space is created as a result of production. The remaining expand to fill the space. Okay, water encroachment from aquifers, that's a water-bearing rock, occurs retarding pressure drops due to production. So this is the effect of your aquifer. It is connected to your reservoir. In part one, we have seen that you can have your aquifer as a linear, attached linearly or at the edge or bottom, at the bottom of your reservoir. So whichever type of aquifer is occurring within your reservoir system, as pressure drops, there is a response from your aquifer. Your aquifer responds, okay, by water influx. Okay, so it's a form of drive. So there is an influx of water from your aquifer to fill up the pore volume left by production of oil and gas from your reservoir. Okay, so the pore volumes left in the microscopic pores, the spaces left there is filled in by the water from the aquifer. So this maintains the pressure of your reservoir. Okay, so your reservoir responds to pressure drops from your reservoir. Your aquifer responds to pressure drop from your reservoir, thereby maintaining the pressure of your reservoir. So this is known as water encroachment. Water encroachment occurs from the water-bearing rock in order to maintain the pressure of the reservoir. Okay, so I'm sure you are familiar with this point as well. Above the bubble point, connate water and formation water compressibilities are small relative to the compressibilities of the reservoir fluid. So above the bubble point, you have the contribution of your connate water and formation water compressibilities to the drive of your reservoir fluid to the surface. But their contributions is quite minimal. It's quite minimal. They, however, account for an appreciable fraction of production above the bubble point. Above the bubble point, yeah. It's quite minimal, but still appreciable above the bubble point, okay? But below the bubble point, that's the last point. Water and formation compressibilities are less significant in gas and gas cap reservoirs and reservoir below the bubble point where there is appreciable gas saturation. So below your bubble point, as soon as you have the evolving of your gas from your reservoir, or you have the presence of your gas cap, your formation compressibility, that your CF, your water compressibility, your CW, okay, are all less significant because you have the presence of gas in your reservoir, either as gas cap or as a solution gas. Okay, so because the gas is highly compressible, so CWCF is far, far, far less than CG. Okay, I believe you can remember this from the previous class where I asked you, I gave you a series of compressibilities and I asked you which is the highest and what does each of the compressibility mean. So if you miss the class, you can go back to the video and watch it. So CG, that's gas compressibility, is far, far, far higher than CW and CF, okay, and more significant. CG is highly significant, especially below the bubble point pressure. Below the bubble point pressure, while CW and CF is, though less significant, but it contributes an appreciable fraction above the bubble point pressure. That's in the undersaturated zone. Okay, so let's go on. Let's look at the limitations of the material balance equation. It cannot be used in a virgin reservoir where production hasn't occurred and there is no history data. So history data, you remember the slide where we discussed in part one, where we discussed the requirements of the MBE. There has to be a history data of that reservoir, okay, that production data of that reservoir. It does not take into considerations the lateral and vertical variations. You remember we said that the reservoir characteristics is taken has been averaging equal, okay, averaging the same all through the reservoir. So it doesn't account for lateral variations and vertical variations. It assumes uniform properties, okay, because it assumes uniform property, it is also a limitation to MBE. Is a limitation to material balance equation. It is highly sensitive to pressure and gas measurements as well. So these are limitations limitations of MBE. Okay, so let's go on. So what are the data requirements? As we move on, we need accumulative oil. You remember where they were listed with their units. So you can also go back to that slide and look at the listings and their units. So we need the cumulative oil, the gas, and the water produced. We need our BO, BG, RS. These are PVTs. I mentioned RS that can be measured in the laboratory, either via flash separation or differential separation. Please read more on difference between flash separation and differential separation. And then pressure, you have build-up tests. You still do more of this in your reservoir journey, different types of pressure build-up tests where pressures are measured, okay? So each pressure point has its corresponding PVT data, okay? And then you need the cumulative GOR produced, which is your NP by GP. You need your cumulative water influx into the reservoir from the aquifer, and then we need the gas cap volume, all data requirements for MBE. Okay, so before I explain this slide, let me okay, here, so trying to see. Okay, this slide. Derivation writing a volume balance equation for our material balance. Remember we said a material balance is a pot model. So the algebraic sum of all what goes on within your reservoir is zero. So here we have the total underground withdrawal. That's production, equals the expansion of oil and dissolved gas. Now, this you should be well familiar with this because I've taken time to lay the foundation of your oil, all the energies in your reservoir, and also your water influx. So by now, I believe you have a basic understanding of all these drives. Okay, so your total underground withdrawal, that's your oil and your gas and your water produced from your reservoir, equals the expansion of oil and the dissolved gas. This is referred to as your A. In this equation 1, you have your F equals A plus B plus C plus D. So your A, the expansion of oil and dissolved gas. You remember? The expansion of the gas cap gas, that's your B. Then you have your C, which is reduction of pore volume due to connate water expansion and rock compaction, okay? Reduction of pore volume due to connate water expansion and rock compaction, that's your C. And then you have your D, which is your water influx. Your D is your water influx. Okay, so your F equals your A plus B plus C and plus D. Your F equals your A plus B plus C. So we'll go to the next slide. Okay, so now this is the pot model. You have your gas cap. You'll see what this means in a moment. You have your gas cap here. You have your oil plus the dissolved gas. Your oil plus dissolved gas. So here, as pressure drops, what happens? You have expansion of your gas cap. So your gas cap was initially here, but it has expanded. Okay, so expansion of your gas cap gas. Your oil and the dissolved gas, you have its expansion as well. Okay. You have the expansion of your oil and the dissolved gas. Okay. And then as a result of the rock and fluid compressibilities, okay, you also have the expansion of rock and the fluid compressibility within your reservoir. And then you have your D, which is your water influx. So study this. I can as well ask you to draw a schematic diagram of your port model, your MBE port model. Okay, so this also explains it better. You have your oil zone and you have your gas zone. This is your initial pressure, PI. Remember your PI. Okay, as pressure drops, this is P as every other P. Pressure drops from initial pressure. What happens? This is your new gas cap volume. Okay, so it has extended. You have your evolved gas. You have your gas injection and water injection. So this is from external to the reservoir. And then you have gas and water injection, which was mentioned earlier, that when you have pressure maintenance, okay, going on, you have either have gas injection or water injection. So rock expansion, you have the remaining oil, okay, and then you have the water, the net water. So all this leads to oil production, your NP, your water produced, and your gas produced. The effect of all this all together. So the net summation of all this should be zero. The net summation of all this should be zero. This is like your inlet minus outlet equals zero. That's why it is a tank model or some tank model. It is a tank model. So your inlet minus outlet equals zero. Inlet minus outlet equals zero. Okay, so this is your total underground withdrawal, your F, and this is your A, B, C, and D. This is your A, B, C, and D, all occurring in here. Okay, so here gas injection and water injection is added. Okay, so this is your F, that's oil withdrawal, water withdrawal, and gas withdrawal. Okay, the fluids which can be produced from your reservoir as a result of your A, effect of your A, your B, your C, and your D, and in some cases, injection. Okay, so this is your tank model. Okay, so you have your F, total underground withdrawal. Your NP is cumulative oil produced in STB. Your GP is cumulative gas produced in STB. Your WP is cumulative water produced, likewise in STB. When oil, gas, and water are produced from the reservoir, what happens? Reservoir volume of oil produced is your NP, STB, multiplied by your BO, RB per STB. Okay, so what do you have here? You have your STB cancels, you have your NPBO, that's your in reservoir barrel, because we want to estimate the reservoir barrel of your oil produced. What are we trying to do here? We are trying to account for the total underground withdrawal. You remember here, let me go back a bit so that you can fully understand. The total underground withdrawal, this is your NP, WP, and GP. Okay, so for your NP multiplied by BO, your cumulative oil produced. Okay, so you have your NP, the total oil produced in STB multiplied by BO. So it gives us in reservoir barrel. We all want them in reservoir barrel. Okay, then reservoir volume of free gas. You have your NP, that's your total oil produced. Okay, RP minus RS, that's your solution gas produced minus your solution gas multiplied by your BG. This is in STB from the formulas requirements I showed us in the previous slide. Your SCF per STB and your BG. BG is in RB per SCF. So all this together gives us, it cancels out, STB equally cancels out, and then you have it in RB. Okay, so for your free gas, you have NP multiplied by RP minus RS multiplied by BG. Okay, then for your water produced, that's the third one. Remember, there are three basic reservoir fluids. The two we are interested in is oil and gas. But fortunately, it's a blessing that God has given us water in all our reservoirs. Okay, so we have oil, gas, and water. So we are accounting for the three. Those are the three fully total underground fluids that are taken from our or produced from our reservoir. So for Water, you have WP, VW. That's the formation volume factor. You will observe that we always multiply by the formation volume factor because that's what gives us the quantity of that reservoir produced in reservoir barrel. Okay, the quantity of that reservoir fluid produced in reservoir barrel. Okay, we estimate it in reservoir barrel so that we know the amount that was actually present at reservoir condition. Do you get that? At reservoir condition. So you have this also in reservoir barrel. So what is our F in essence? Okay, just a minute. Our F, bringing all these three together, is our oil produced. This is our gas produced. You know why we are removing RS? Because RS is the solution gas still left. Okay, the solution gas in your oil. Okay, so we remove it from RP, gas produced. Okay, so to give us the actual gas produced, gas oil ratio produced. Okay, so this is the gas produced, fully gas produced, that's NP multiplied by RP minus RS multiplied by BG, and this is the water produced. So this is oil, this is gas, and this is water, which is our F. Okay, so this is equation 5. I hope you can see that. Okay, so let's go to derivation of our A. Derivation of our A. A is expansion of oil and its dissolved gas. Expansion of oil and its dissolved gas. Your N is stock tank oil initially in place in STB. Stock tank oil initially in place in STB. And then your initial oil in the reservoir, that's converting it to RB, reservoir barrel. Remember I said we want to estimate them in reservoir barrels. So initial oil, that's N multiplied by BOI, because this is the initial oil formation volume factor, NBOI. And then initial oil in place after expansion, that's N multiplied by BO, that's RB multiplied by STB, that's NBO. So you have NBOI and you have NBO, okay? So what will be the expansion of oil? Because your A is expansion of oil and its dissolved gas. So we want to look at the expansion of oil and the expansion of dissolved gas together, because we believe that there is an energy that the expansion of oil and dissolved gas provides to your reservoir. Okay, if you check the part 1 of this topic, where I showed you the schematic diagram of different wells under combination drives. So expansion of oil and its dissolved gas, you have N, you have your N, this should be NBOI, okay? NBO minus your NBOI. NBO minus your NBOI. So you have your N into BO minus BOI. You collect that your BO is higher than your BOI. Okay, when we did your pressure BO plots, your BO is higher than your BOI, the oil formation volume factor. Okay, okay, so you have N into BO minus BO minus BOI. So you remember that because of a slight expansion from BOI to BO is higher than your BOI. Okay, so this is the expansion of oil. Okay, so aside, we try to break down your BG, reservoir volume of gas is in reservoir barrel per STF, and surface volume of gas is in SCF. Okay, so from your ID gas law, you recollect this. You recollect your PV equals nRT, your ZSC, that's your compressibility factor is 1 at standard condition. Gas compressibility factor standard condition is 1. Your PSC pressure at standard condition, your temperature at standard condition, 520 degree Rankine. and then your P1V1 over Z1 T1, you have it VSC, PSC, VSC, ZSC, TSC. So if you go through this, you remember your BG is your VR over VSC. That's your reservoir volume over VSC, volume at standard condition, which gives you this, And then your BG, if you rearrange the reservoir conditions and the standard conditions at the surface, so you have this. And then you can relate your V2 over V1 to VSC, BG2 over VSC, BG1. So in essence, you can slot in the PSC, ZSC, TSC, okay, to obtain the value that you have here, okay, value that we have here. Then you'll be given your Z, your T, and your P in order to calculate your BG. So it shows relationship between your BG and your ideal gas law. Okay, so let's look at the initial gas oil ratio. You remember that we are looking at A, expansion of oil and dissolved gas. We have looked at the expansion of oil, and then we want to look at the expansion of the dissolved gas. We started by looking at how our BG is connected to our gas law. Okay, and then okay, so the initial gas solution gas ratio, RSI, final gas ratio, gas oil ratio, RS, at every other pressure, total dissolved gas initially, so to be your N, that's your initial oil in place multiplied by RSI, your total dissolved gas after expansion, N minus RS. You remember when we did that of oil, we also multiply by BO. So in this case, because it is gas, we are multiplying by RS, okay? Expansion of gas is therefore N RSI minus RS. We know in case of gas oil ratio, RSI is greater than RS. So it is NRSI minus NRS, which gives this. Then multiply by BG in order to give us in reservoir barrel. Okay, so expansion of oil and its dissolved gas is therefore the oil component and the gas component. The oil component and the gas component. So you have N into BO minus BOI plus RSI minus RS BG, okay, collating them together. So that is adding equation, you have equation 6 and equation 9. Equation 6, where you have NBO minus BOI, that's the expansion of your oil, and the expansion of your gas, NRSI minus RSBG. Okay, so you have it here. This is expansion of oil and its dissolved gas. Okay, who can guess that's your A that you have here. Expansion of oil and its dissolved gas. We have looked at the total underground withdrawal, which is our F. We have looked at expansion of oil and its dissolved gas, which is our A. Now we are going to expansion of the gas cap gas. Expansion of the gas cap gas, which is our B. Okay, so I'll run to the slide. Okay, so here, expansion of the gas cap gas. Gas cap gas. Remember, your gas cap also provides an energy to your reservoir as a result of its high compressibility. Remember, your CG is far high. Okay, so now your initial oil volume is NBO high. You can recollect this from your A, NBO high. Okay, your gas cap size is gas cap volume over oil volume. So your gas cap, your M is gas volume over oil volume. Gas volume over oil volume. Okay, you can take it like that, gas volume over oil volume. Okay, so you have, because you have your initial oil volume in place, MBO high. So you have your oil volume fixed here. Your M is gas cap volume over oil volume. Okay, so your initial gas cap volume, GBG high, that's your G multiplied by BGI. Okay, but you can still take it as the initial gas cap volume. Your M multiplied by this, NBO high. Your M multiplied by this. So you have your initial gas cap volume as equals MNBO high in reservoir barrel. Okay, remember this is dimensionless, your M and your NBOI. You can check the previous slide from where we estimated our NBOI from our A. Okay, so this is your initial oil volume, NBOI, initial oil BOI multiplied by your M from this relationship, okay, in reservoir barrel. Okay, so let's go on. As the reservoir pressure drops to a new level, the gas in the gas cap expands, okay, and occupies a larger volume. Assuming no gas is produced from the gas cap during the pressure decline, the new volume of the gas cap is given as. Okay, so let's look at this. You have your G equals MNBOI over BGI. Okay, remember that your BGI equals MNBOI. Your BGI equals MNBOI. Okay, from here. Okay, from here, this is your GBGI, Isha, equals MNBOI. Okay, equals MNBOI. Then volume of gas cap at pressure P, as every other pressure, you have MNBOI over BGI multiplied by your BG, okay, at pressure P. So that's MNBOI over BGI, okay, multiplied by your BG in reservoir barrel. This is your equation 14. So your gas cap expansion is your equation 14 minus equation 13. This is at every other pressure, okay? This is at every other pressure. So if you take your equation, this is your equation 14. If you take your equation 13, here's equation 13, MNBOI. That's the initial gas cap volume, is MNBOI. Then at every other volume, you have it here over BGI. So if you remove MNBOI over BGI minus MNBOI, that's equation 13. So you have MNBOI over BGI minus MNBOI. So if you make MNBOI your subject of formula, you have BG over BGI minus 1, all in reservoir barrel. All in reservoir barrel. So this is gas cap gas expansion. This is your gas cap gas expansion. Okay, I hope you understand that. Okay, so let's look at our C. Our C, we have done A, we have done B, now we're going to C. Your C is reduction in hydrocarbon pore volume due to rock compaction and connate water expansion. So your C, your oil volume is still NBOI, you remember. Your gas cap volume, from the relationship of your M, you have your MNBOI, that's the gas cap volume. Your total hydrocarbon volume will be your oil plus your gas. Your oil plus your gas, that's 1 plus M NBOI. Okay, so if you add this and this together and make NBOI the subject of formula, you have 1 plus M into NBOI in reservoir barrel. Okay, so the C we are considering is reduction in hydrocarbon pore volume due to rock compaction and connate water expansion. Due to rock compaction, that's CF, and connate water expansion. Okay, so you have saturation. We go to saturation. Okay, your hydrocarbon saturation, volume of your hydrocarbon over pore volume. So your SHC equals 1 minus SW. So here, your SHC, your saturation for hydrocarbon is summation of your oil and your gas. That's SO plus SG. Okay, but we are saying here that less SHC represent the summation of your oil and your gas. So if you take your oil and your gas out, what do you have left? You have 1 minus SW. Okay, so your SHC, that's the saturation of your hydrocarbon, equals 1 minus SW. So if you take SW, that's saturation of water, out, you have oil saturation. You have oil saturation. Okay, so your pore volume, your pore volume, if you rearrange this equation 17, you have your volume of hydrocarbon over saturation of hydrocarbon. So your pore volume multiplied by SW, your pore volume multiplied by SW equals volume of your hydrocarbon. Volume of your hydrocarbon. Okay. Okay, so I made a bit of correction here. Your pore volume, because you have SHC here, saturation of hydrocarbon is 1 minus SW. So your pore volume multiplied by 1 minus SW is volume of your hydrocarbon. Okay, so let's go on. Don't forget that we are trying to estimate C. What C? We've done A, B, and now we are on C. So our hydrocarbon pore volume is 1 plus M NBOI that we have here. Okay, let me go back a bit. Okay, 1 plus M NBOI, that's your total hydrocarbon volume. Okay, divided by 1 minus SW. Okay, from equation 18. Pore volume of hydrocarbon, which is 1 plus M NBOI over a saturation of hydrocarbon, which is 1 minus SW. And we're using SW, 1 minus SW, because most of the time, saturation water data is available. Okay, it's readily available. So 1 minus SW usually used. Okay, so let's recall that our C is minus 1 over V dVdP. Our CF, therefore, rock compressibility, dV will be CF VdP. Your dV, CF, your V, that's the hydrocarbon pore volume. That's what you have here, hydrocarbon pore volume, dP. So our dV, okay, volume change due to rock compaction. Remember that your C is reduction in hydrocarbon pore volume due to rock compaction and connate water expansion. Okay, so volume change due to rock compaction. So you have your hydrocarbon pore volume. Okay, so here in equation 20b. So here, this volume change due to rock compaction, CF. Okay, so you have hydrocarbon pore volume, which you have in equation 19. Substitute equation 19 here. 1 plus M NBOI over 1 minus SW. Actually, this should be equation 19. Check. Yeah. Still, yeah, equation, this is the total hydrocarbon volume, 1 plus M NBOI, equation 16. Okay, so then divided by 1 minus SW, which we generated in equation 19. That's the total hydrocarbon pore volume. Then you have your dP. The dP you have here. We have been able to come up with this hydrocarbon pore volume. This is your CF. This is the relationship for HCPV hydrocarbon pore volume, which we have here. Okay, and this is your dP, same dP you have here. So I hope you understand. Okay, let me move this up here so that okay. So this is volume change due to rock compaction. Volume change, your minus dV due to rock compaction. Okay. So let's look at volume change due to connate water expansion. Volume change due to connate water expansion. So this is CW, VW, dP. Then you have your PV. Your volume of water is PV multiplied by SW. Multiplied by SW from the relationship of your oil and here pore volume from this equation 18. Your pore volume PV is volume of hydrocarbon over saturation of hydrocarbon. So if you have volume of water over saturation of water, that's your pore volume. Okay, your water saturation Okay, let's start from here. 17, your water saturation will be volume of water over pore volume. So your water saturation, PV multiplied by saturation of water, will equally be volume of your water. Okay, so that is what you have here. That's what you have here, PV multiplied by SW. Okay, and then if you insert equation 16, the PV pore volume is 1 plus M NBOI. 1 plus MnBOI. Okay, remember your pore volume. 1 plus MnBOI. Okay, so you have your CW multiplied by your PV multiplied by your SW and DP. Okay, remember we generated 1 minus SW together for the PV. Okay, let me move this up here. So your change in hydrocarbon pore volume is summation of your reduction in hydrocarbon pore volume due to rock compaction and your connate water expansion. So you have Harding equation 21 and 23. Equation 21 and 23. So I want you to write out these equations and actually do the additions yourself. So on adding it, you will have the change in hydrocarbon pore volume, okay, as a result of connate water expansion, okay, and rock compaction. What do you have? You have the common factors, 1 plus M NBOI, okay? And you have the non-common factors to be your CWSW plus your CF. CWSW plus your CF, okay? If you had your 21 and 23 divided by 1 minus SW. So that makes your C, your C. So we have successfully explained what A is, what B is, and what C is. Now let's go to D. D is simply your water influx. D is simply your water influx, WE in reservoir barrel. That's all. For your D. Okay, so you have substituting all times into your material balance equation, your F, which is underground withdrawal, you have your A, you have your B, you have your C, and you have your D. So you have the equation 25. To the left-hand side, you have your F, and to the right-hand side, you have your A plus B plus C plus D. So your F, your oil component, your gas component, and your water component, all withdrawn from your reservoir. Remember, it's a tank model, and the algebraic sum of the underground withdrawal and the components of your reservoir, which balances the energy within the system, is 0. Okay, so the algebraic sum is 0. Here you have the expansion of oil and the dissolved gas. Remember that happens, expansion of oil and dissolved gas. You have the gas cap gas expansion. You have the expansion due to rock compaction and the connate water. Okay, and you have your water influx. So the derivation of our A, derivation of our B, derivation of our C, and the derivation and the D, which is the water influx. Now, when you have pressure maintenance, you remember where you have the water injection and the gas injection. So all that comes to your left-hand side because it is what is coming into the reservoir. Okay, so it comes to the left-hand side. Remember, your F is withdrawal. Okay, your N is within the reservoir. So withdrawal minus what is within the reservoir equals 0. Okay, equals 0. That's the tank model, the zero-dimensional model. Okay, so your injection comes here, so it is added to your water influx. So if you have water injection, you have your water injection multiplied by BW. Remember, that's why this converts it to reservoir barrel, and this also converts it to reservoir barrel, gas injection. So you have the water injection component and the gas injection component. So you have your material balance when pressure maintenance is going on to be this, equation 26, and you have your material balance without pressure maintenance to be your equation 25. Okay, so this is the part 2. I'll be stopping here, and I'll see you in part 3 of this class.